Okay, so it is my pleasure to introduce the next speaker, Professor Bong Lian from Brandeis. Will speak on, so his talk is called From String Theory and Moonshine to Vertex Algebras. I want to mention that I studied Vertex algebras together with Bong as graduate students about 30 years ago at Yale. And it's my pleasure now to, 30 years later, to introduce you. Please.
Thank you, Pavel. I'd like to begin by saying that I would dedicate this lecture to the memory of John Conway, who unfortunately passed away on April 11, succumbing to COVID-19. All right, let me start by acknowledging a few people. Much of what I talk about was partly developed and partly learned with some of my former collaborators, Andy Linshaw, my former graduate student, Bai Lin Song, who is also my former student at Brandeis, and Greg Zuckerman, my former advisor. Also, the formation of this lecture, I received quite a bit of assistance from my colleague An Huang, and especially my postdoc TJ Lee, and Andy, of course. Okay, all right. So next, a disclaimer. So this is meant to be a very brief survey of a short period prior to and soon after the creation of the theory of vertex algebras. And I, of course, make no claim of completeness of this lecture. This is not meant to be a comprehensive survey of the theory of vertex algebras. I could only highlight some of the developments that reflect my own views and biases about the subject. So again, since it's a brief history, early history, I will have to leave out a lot of very important topics, including things like geometric Langland, tensor categories, and so on. All right. The format of my talk will be sort of, I place the emphasis on the cross influences between physics and vertex algebras during a very exciting period of their current development. And the talk will be non-technical and yeah, because it's for general audience. Okay. All right, so this is an outline. I will try to at least do the first three parts, and if I have enough time, I will say something about some of the speculation Greg and I developed in the 90s and in 2000, early 2000s. So I will start with the early history during the 20-year period. And I call it two parallel universe because it literally is a couple of parallel development that doesn't talk to each other early on, one in mathematics and one in physics. And then when I start to describe the moonshine, I will return to a perspective that I partly helped develop along with Greg Zuckerman and independently with Haixing Li, that view a vertex algebra as some kind of higher commutative algebras. And we found that this point of view makes the theory very, very easy to work with and understand, and it's a point of view that is in our view very robust and logically equivalent to the older perspectives. Part three of my talk will talk a little bit about cousins of the moonshine, the famous Moonshine VOA, work that primarily started by Schellington in the late 80s, and then many mathematicians pick it up. And now it's almost the classification problem is almost complete. So I think it's a beautiful story that I want to touch on, especially because of its close relationship with the Moonshine VOA. Okay, all right. All right, so let's start with the late 60s. So in the late 60s, people were trying to come up with a theory of strong interactions. Two very interesting aspects of strong interactions, specifically meson scattering. People observed that there is something called S and T channel crossing symmetry for the scattering, for meson scattering amplitude. And also there is something called the Regge trajectory, which is basically a plot of angular momentum versus binding energy for the Coulomb potential in a non-relativistic quantum mechanical model of for meson scattering. So there were some interesting features about these two things, but it's only empirical. And Veneziano was trying to give a mathematical model that explained these phenomena. And the model that he introduced involved using something called the Euler beta function. And the reason he used that is because the Euler beta function precisely has this exchange symmetry involving S and T channel. And it also partly explained the Regge trajectory. Without going into the technical detail, suffice to say that this was pretty much the starting point that of the development of string theory. Because soon after Veneziano, Nambu, Nielsen, and Susskind provided the first interpretation of this Veneziano amplitude using Euler beta function in terms of representation theory. Namely, they show that you can reproduce Veneziano amplitudes by using a Fock space representation of infinitely many harmonic oscillator. And that was also later generalized from 4 particle to n particle. And the amplitude was written in terms of correlation function of the first example of vertex operators. Something look like the normal order product or the Wick product of an exponential of the momentum vector dot with a multi-component scalar field phi. And this operator is supposed to act on Fock space of free bosonic field of a string. Now the string interpretation was actually a couple of years later given by Goddard and his collaborators. And in 1974, Shirk and his collaborator went one step further and say that in fact this should be part of a fundamental theory of strings, and that this theory of string is capable of producing fundamental particles of arbitrarily high spin as string resonances, and gravity is also part of this theory, being the spin 2 particle. So there was a brief hiatus after Shirk et al., and it was basically during this period a game that's played by a small niche of diehard string theorists. Very few people pay attention to it until the early 80s, when Polyakov proposed a path integral formulation for the bosonic string theory. Again, I have glossed over and in fact skip over a number of interesting development in the late 70s. Those I would have to refer you to the original literature. The best one being the introduction in the Green-Schwarz-Witten Introduction to the String Theory 2-volume book for more details of this development. In any case, in the early 80s, Polyakov introduced the technical formulation of the bosonic string theory, and also explained why this theory quantum mechanically only lives in 26 dimensions. Few years later, Belavin, Polyakov, and Zamolodchikov proposed what they call a conformal bootstrap program to systematically study two-dimensional conformal field theory as a classical string vacua and models for universal critical phenomena. So, for example, the Ising model and the likes are examples in BPC theory. Part of this theory, part of the highlight of this theory was that they introduced a very powerful mathematical formalism called the operator product expansion for two-dimensional conformal field theory observables. So this is this formalism is actually standard in physics, but for mathematicians, this turns out to be a extremely useful and powerful tool for later. Okay, so here's an example of what BPC introduced: the Virasoro OPE of a two-dimensional conformal field theory. So if one looks at the left-moving two-dimensional stress-energy tensor, call it T of Z, of central charge C, and C be also called a conformal anomaly, then the operator product expansion is given by this box equation. So the leading term has a fourth-order pole in the short distance expansion of Z approaching W, and so on. The rest of the term following the ... are all regular terms. So you can use the OPE to formalism to work out the singular terms, and the singular term pretty much characterize how this stress energy tensor behaves in this particular conformal field, in any particular conformal field theory. Okay. And then shortly after BPZ, there's a sort of an explosion of activities. I still remember 1985 was my first year in graduate school at Yale. And this is a time when virtually every high energy physics PhD would look into the possibility of working on string theory. So there was a huge amount of activity leading to a new generation of physicists to learn the theory, and part of the most of the efforts is try to organize and catalog two-dimensional conformal field theory using representation theory of something called chiral algebras. What is a chiral algebra? Well, the chiral algebra of a conformal field theory consists of all the left-moving operators. So all the operator that only depends on a single complex parameter and not its complex conjugate. So these are called left-moving operators. And there's a particular class of these conformal field theory whose chiral algebra are called rational, in a sense that they only have finite number of irreducible representation. In cases like that, physicists discover that, at least empirically, that something called their representation theory can be used to very close to characterizing the underlying conformal field theory up to some finite number of choices. And these characterizations involve something called the fusion rules. So let me give you a few examples. So for example, the BPZ classified the Virasoro central charges and the highest weight of the rational minimum models. So these are conformal field theory whose chiral algebra is generated by a single left-moving operator, namely the two-dimensional stress energy tensor, which is on top of this page that I'm showing right here. And the main tool that BPC used was the famous Katz-determinant formula for the representations for the Verma module representation of the Virasoro algebra. So BPC proposed this classification. It wasn't quite become a it hasn't quite become a theorem until much later, following the thesis of Yongcheng Xu, a student of Igor Frankl at Yale, and a student of Victor Katz, Weijing Wang, a number of years later. That finally settled that this classification. Okay, another class of example is the famous West-Miller-Witten model that are characterized basically by unitary representation of loop groups of compact groups. So the models started with early work of West and Zumino, and Witten reinterpreted the theory in terms of representation theory of loop groups. And so this gives another beautiful class of rational two-dimensional conformal field theory. Another notable class is was proposed by Goddard, Ken, and Ollis, using what they call coset construction for compact Lie groups. So I will have a little bit more to say about coset construction later when I discuss some of the work that Linshaw has done in this direction. So I'll return to the last class of example.
Sorry, excuse me, Ron, sorry to interrupt.
Yes.
It appears you're accidentally covering your camera with your finger. I don't know if you're saying that you're doing
I apologize. All right. Okay, my apology. Okay. Okay, so the next important development was a series of seminar papers by Moore and Seiberg in the mid and late 80s, where they introduced the so-called duality axiom for conformal field theory that pretty much crystallized many of the early ideas that starting from BPZ on. And so for chiral algebra, the duality axiom implied, for example, that the matrix coefficient of correlation functions of any left-moving operators admit a meromorphic continuation on CPU1. And most importantly, the operator products are formally commutative after analytic continuation. And the simplest example would be if you take the matrix coefficient of the stress energy tensor, T of Z, with itself, and take the vacuum expectation value, meaning you sandwich it between the highest weight vector, say in one of the BPZ minimal model, and then compute the matrix coefficient, you would get this simple fourth order pole. And you see that from this formula, this function is, if you interchange Z and W, you see that this function, the analytic function, this meromorphic function doesn't change. So it is as if T of Z and T of Z and T of W commute with each other. But this is this commutativity is only in the sense of analytic continuation. It's a sort of a subtle form of commutativity. So this would be a point of view that I will later emphasize and make use of to explain and illustrate the construction of Moonshine, among other things. All right, now comes the second of the parallel universe. So this is the Moonshine universe. I've explained the physics universe earlier in the first part of my talk. This is the Moonshine universe, starting with a remarkable observation by John Mackay in 1978, where he found evidence of an existence of an infinite dimensional Z-graded representation something called V natural, of a hypothetical finite simple group called the monster group, which throughout this talk will be denoted by this boldface M. This group was predicted by Fisher back in 1973 during the height of the classification program for simple finite groups. So particularly, Mackay's observation was that if you look at the Q extension of the modular invariant function, the J function, you will see that the numbers are all positive except the coefficient of Q to the 0. So with the leading term of Q to the -1. And that Mackay observation was that these coefficients can be nicely partitioned into sums with non-negative coefficient of the dimension of the representation, irreducible representation of the monster group, of this hypothetical monster group. Apparently, people know how to, before they know how to construct a group, they know how to calculate the dimension of its irreducible, at least the low-lying irreducible representations. And one see that the coefficients of J of Q have very nice partition into these dimensions, which I call R1, R2, and so on this slide. So I believe Robert Grice in his lecture a couple of weeks ago have also mentioned part of this development. So I'm repeating some of what he's saying. Okay, all right, so next up is Thomson. So Thomson observed when Mackay communicated his observation to Thomson, he saw that the J of Q can be thought of as the Q trace, or the Q trace of the identity operator on this hypothetical module V natural. The Q trace is defined formally as, well, it's a graded dimension graded by integer. So you take each graded pieces and you take the trace on each graded piece of the identity operator 1, and you multiply that trace by the power Q to the n, okay? Where n is the grading for that particular piece. So this was Thomson's interpretation. This remarkably would later become the genus 1 partition function of a holomorphic vertex algebra underlying this V natural to be constructed later. And so Thomson also made the following proposal that that if the Q trace of the identity operator is so interesting, then one should expect that if you take a general element of this monster group, if it exists, that should also be a very interesting Q series as well. And in fact, Conway and Norton, following Thomson's suggestion, computed the leading terms of these hypothetical Q series, again, before knowing that the group M exists. And they saw that these Q traces, in fact, agree with, are in fact very interesting functions because they agree with the Q series of a very special class of genus 0 modular functions. And they gave a complete list of these functions that represent all the conjugacy, the trace of all the conjugacy classes of the hypothetical group M. These traces, this Q series, are now known as the Mackay-Thomson series, which I denote by TG. So G being an element of the monster group M. And so that gave birth to what is now known as the Conway-Norton-Moonshine conjecture, which states that there exists a graded M module, V natural, having the Mackay-Thompson series TG as its Q series. All right, now comes the 1980. So Robert Grice announced his construction of the monster group. So finally, the largest sporadic finite simple group is born, thanks to Robert Grice. And Grice constructed this group as the full automorphism group of what's now known as the Grice algebra. It's a commutative non-associative algebra of dimension 196,884. Again, this I'm sure Robert explained in his May 6th lecture. This algebra, as you will see, later become one piece of a much more elaborate structure called the Moonshine Vertex operator algebra, V natural. Right, now concurrent to this finite group development seems to be an emergence of a theory of representation for a large class of interrelated infinite dimensional graded algebras. Examples of which include the Virasoro algebra, Katz-Moody Lie algebras, and also some sort of nonlinear analog of these algebras, or W algebras, and there are various coset constructions. So this is sort of an emergence of a new type of representation theory, if you will. Okay, let me mention some specific important examples. So in the 80s, 1980, Frankel and Katz gave the first construction of the so-called level 1 irreducible representations of affine Katz-Moody algebras using free bosonic vertex operators. I denote here by E subscript alpha, which are parameterized by an even lattice L. These turns out to be the analog of what physicists earlier talked about, the ones that Nambu and company proposed as a vertex operator. That's no more the product of an exponential sum. The construction of Frankel and Katz focus on the case where L is the weight lattice of ADE type, also called a simply laced root system. Okay, next. In 1986, Borchertz published a paper in which he axiomatized the mathematics algebra. And the definition he gave is by means of an infinite set of linear operator identity, basically indexed by integers. So these are honest linear operator on ordinary vector spaces, but they satisfy a very complicated set of nonlinear identities. A couple of years later, Frankel, Lapowski, and Merman, so this is Eagle Frankel, gave a new definition, which they call vertex operator algebras. And the slight difference of term means that the FLM formalism includes an additional structure, meaning, namely the Virasoro, these vertex algebra admit an additional structure given by the Virasoro action of an Virasoro algebra. Basically, this algebra contains as one of the vertex operator the two-dimensional stress energy tensor T of Z, which BPZ used in his 1984 paper. The FLM definition is based on the so-called Jacobi identity for formal power series. It turns out FLM and Borchertz formulations are logically equivalent. So except for this minor technical difference of having the additional Virasoro structure. So if you take out the Virasoro structure, the two formulations are basically equivalent. However, many people view that the FLM formulation is technically and conceptually a bit easier to work with than Borch's original definition. All right, so FLM also gave a general Fock space construction in their 1988 book of a class of vertex operated algebra, VL, based on any even lattice. So this, in effect, generalized the Frankel-Katz construction from an ADE lattice to an arbitrary even lattice. And they also talk about the VOA counterpart of what physicists call orbifold conformal field theory. So in which they gave the first example of a Z2 orbifold using the notion of twisted vertex operators. I will say a little bit more about this later when I talk about Moonshine. Okay, so it turns out that you need this Z2 orbifold to produce the Moonshine VOA with a correct partition function. Okay. In 1992, Borch announced his solution to the Conway-Norton conjecture, and of course, the FLM construction of the Moonshine VOA play a central role in this proof. After all, the Moonshine conjecture is about the existence of V natural having a particular property of Q traces. So V natural, therefore, is the whole construction play a central role in Borch's solution. All right, so now let me move on to give you a brief outline of how the Moonshine VOA can be constructed. And I will use a formalism that I co-developed with my former advisor Zuckerman and independently by Haixing Li in the early 90s. And you can find details of this in a series of papers that the two groups wrote in this period. All right, so first let me start with some notation. Let V be a Z-graded vector space, and the graded pieces will be called V of n, V square bracket of n. And all vector spaces are always over the complex number. So V of n will be called the weight n subspace of V. V star is the graded dual of V, or the restricted dual sometimes called. So this is the direct sum of the dual of the graded pieces. And throughout my lecture, ZW will denote formal variable, and this will eventually take value in the complex plane C. These formal variable will be assigned a weight of -1, and you'll see why that's such a important convention. Integers like integer notation K, M, and N will denote arbitrary integers. All right, so let me first start with a formal power series, which I call A of Z. The coefficient will be called A bracket of N. And right now, I don't care where this coefficient lives. Suffice to say that the live in some linear space. And I want to do introduce some operation on formal power series. So the first operation is I want to be able to formally differentiate it, which I call partial of A of Z. So this will be the formal derivative with respect to the formal variable Z of A of Z. I also want to be able to integrate, which is the formal residue of A of Z. So that's just simply picking out the coefficient of Z to the -1, which in this case happened to be A of round bracket 0. So A of round bracket 0 does not mean A evaluated at Z equals 0, okay? This is the 0th coefficient of Z to the -1 in the formal power series of A of Z. Next, and this is a very important and subtle notation. Let's look at this binomial function, z minus w to the power k. So this expression should be treated only as a formal expression. When k is not negative integer, this is of course a polynomial if you expand it. And however, when k is negative, this is not meant as an analytic function, but rather this expression means exactly what the next line says. It is meant to be the binomial expansion in the region for this analytic function, for this meromorphic function, where the absolute value of z is strictly bigger than the absolute value of w. So, so the right-hand side of this expansion indicates that. So this is the binomial expansion of z minus w to the power k. This expression of meromorphic function simply means its formal power series expansion of this type. So this is important to keep in mind, because when k is negative, this cannot be treated as ordinary meromorphic function. So for example, z minus w to the power minus 2 and w minus z to the minus 2, while they are the same as meromorphic function, they are not the same as binomial expansion. Okay. Next, I want to introduce a space of formal power series as follows. I call it C0 based on the space V. So what is C0? Script C0. So C0 is the space of all weight homogeneous linear maps, which I typically denote as A of Z, from V into the space of Lorentz series with coefficient in V. So V of double bracket Z. The weight, so weight homogeneous means each element of this vector space C of 0, each homogeneous element is assigned a weight. So for example, A of Z is called weight K if and only if it maps the graded pieces, it shifts the weight of the graded piece by the amount plus K minus N minus 1. Each coefficient A of N would have this particular shift in the weight. Okay, so this is the definition of weight. So this makes it consistent with the fact that the variable z is assigned the weight minus 1. So if you look at the formal expansion of A of z and take into account the fact that the variable z has weight minus 1, then A of z literally has weight weight k in this case, provided that its coefficient A of n has this particular shift in weight on each of the graded pieces of V. Okay, next piece of definition. So this is the key definition to the circle algebra formalism. I introduced what we call the nth circle product on the space C of 0. So take two elements of C of 0, call it A and call it B. I define a bilinear operation called A circle NB, one for each integer n, by this residue formula. Okay, so I take the formal power series A of Z and B of W, two different variables, multiply it by this series expansion Z minus W to the n. Again, n can be positive or negative or 0. And then I expand this in the way I prescribed earlier. And then I take the coefficient of Z to the minus 1 in this expansion. That's the first term of the circle product. The second term is defined in a similar way, but with W and Z interchange. Okay. Now, if A of Z and B of W were ordinary scalar value meromorphic function, then this would literally just be the complex analytic residue of that scalar function by taking the residue along a contour around z equals 0. So let me illustrate that a bit. So first, note that it's not hard to check that C of 0 is closed under all circle product, meaning if A and B are element of C of 0, then all their circle products, A circle and B, are also elements of C of 0. And obviously, C of 0 contains 1, and as I said, C of 0 is closed under all circle product. So any subspace of C of 0 that is containing 1 and closed under the all circle products is called a circle algebra. So, so for this class of algebra, you could then talk about homomorphisms and modules without any difficulty. So once again, a circle algebra is simply a subspace of C of 0 that contains 1 and is closed under all the circle products. So this is sort of an obvious way to define this algebraic notion. All right. Now comes another important property, important notion. I say that two operator A and B in C of 0 circle commute. So this is not strictly commute, but circle commute if it has the following property. You take the formal commutator of A of Z and B of W. So what you get is a formal power series with two variables and whose coefficients are linear maps on V. Take this power series. This power series in two variables. Suppose you can find a polynomial of two variables of the form z minus w to a power n, where n is sufficiently large, that annihilates this commutator. Then you say that these two operators A and B circle commute. Notice that this equation is very subtle, because you might ask, if this is the case, can I not just invert z to the minus w to the power n and show that this condition implies A and B strictly commute? The answer is no. And the reason it's no is because the space of formal power series is not a module over the space of formal power series. Exactly because you cannot always multiply two formal power series because of algebraic divergences. However, the space of formal power series is a module over polynomial ring. So it makes sense to multiply a power series by the polynomial z minus w to a power n, provided n is non-negative. Because in that case, that function is in fact a polynomial function. So this condition makes perfect sense mathematically. All right. So you can have two operators that circle commute without strictly commuting, as I will give some examples later. All right. Let me make a few remarks. If I take a linear function u star and a vector v, and consider the matrix coefficients v star of the operator A of z and B of w between these two vectors u star and v. Then circle commutativity guarantees that these two matrix coefficients actually converge to the same rational function, not just meromorphic, but a rational function, which I'll denote by f of AB, because they clearly depend on A and B linearly. And this is a rational function in two variables, z and w. In fact, it's not hard to show that circle commutativity guarantees a certain form of this rational function in the following way. All the possible poles are along z equals w, or z equals 0, and w equals 0 in the respective region, absolute value of z bigger than w, and the other way around. So it turns out that this statement that these two matrix coefficients converge to the same rational function in two different regions, non-overlapping region, with these poles, this condition is actually equivalent to the algebraic condition of circle commutativity. So circle commutativity somehow has a dual interpretation. You could interpret it complex analytically using this analytic continuation, and as well as this algebraic commutativity condition, that the formal commutator is annihilated by a certain polynomial. Second remark, we shall write the matrix coefficient by dropping U star and V when the two vectors U star and V are not important. Okay, that makes the notation a lot more clean. All right, third remark, if A and B circle commutes, then it makes computing their circle products very, very easy. So, and here's why. In fact, one can easily show that the circle product, you can read off the circle product by simply taking the formal power series expansion of the rational function f I introduced earlier, and expand it in the power of z minus w. So sort of a short distance expansion. This is precisely the short distance expansion that BPC talked about earlier in their 1984 paper. So if you expand this matrix coefficient in power of z of w, the coefficients in terms of w would be precisely the circle product of A and B. So this gives you a very powerful way and very quick way to compute all circle products simultaneously. Once you know the rational function, you can just extend it formally, and you can read up all the circle products. Okay. So formally, you could look at the bottom of this slide. So A of z, B of z, you could even drop the bracket and simply write it as formal power series with coefficients in the circle product without the bracket. It's understood that this is meant as an expansion of rational function where the bracket is there, but the bracket is in some sense sort of irrelevant because it's universal. One more important note. What I wrote down on the bottom of this slide, the last term involved a weak product of A of z and B of w. So this term is turns out to be always a regular term, meaning there's no singularity as you set z to w. So what's important is the leading singular term in this operator product expansion. The weak product is a universal term that is the same for every it's formally the same for every pair of operator A and B. Okay. All right. So that would be the convention I would adopt. So from now on, I would drop the universal term. Whenever one writes the OPE, one only writes the singular term, following the physicist convention. So, but at least now the physicist convention has a precise meaning in this formalism. It simply means that you're writing all the circle products with non-negative coefficients. Circle 1, circle 0, circle 1, circle 2, and so on. Okay, up to the highest power term. Z to the minus to the power minus n minus 1. Okay. All right, so here's an important result of Dong. It says that if you have three operator in C of 0, and if each pair of them circle commute, pairwise commute, so A circle commute with B, A circle commute with C, and B circle commute with C, then the circle product of A and B also circle commute with C. Okay, so this shows that if you take a set of pairwise circle commuting operators and let them generate a circle algebras by taking all possible circle products among the operators and include the operator 1, then what you get is, of course, a circle algebra. What Dong's lemma implies is that this circle algebra is in fact a circle commutative algebra, meaning any two elements of this circle algebra circle commute. Okay, so this gives a very interesting and easy way to construct circle commutative algebra. So what it says is that all you have to do is you gave me a bunch of circle commuting operators. I can give you right away a CCA, a circle commutative algebra. All you have to do is just take all possible circle products. Okay, so therefore, constructing CCA become a very easy game to play. So let me illustrate with one simplest example. Let V be any highest weight module of the Heisenberg algebra. By that I mean the Lie algebra satisfying this bracket relation I write down in the middle of the page. So A of n and A of m bracket is a scalar, n times the canonical delta times unit, where n and m takes value in the integers. So take this Heisenberg algebra and let it act on any highest weight module. Then you can form the operator A of z by taking the formal sum, this power series sum, whose coefficients are now linear maps on V. Okay, so this A of n. A of n, because V is a module over the Heisenberg algebra, A of n now acts on the vector space V. Now with this operator, with a two-line calculation with OPE, one can easily show that the formal bracket of A of z and A of w with itself is the formal power series on the right-hand side. Notice that this is the difference between two formal power series. One says z minus w to the power minus 2. The other is w minus z to the minus power 2. Formally, these two terms cancel, but because they are power series, they are not the same, and therefore the right-hand side is non-zero. So A of z and A of w do not commute strictly. However, if you multiply the right-hand side power series by z to the minus w, z minus w to the power 2, you see that it cancels both of these terms and you get 1 minus 1. So that condition implies in particular that A of z circle commute with itself, even though it does not strictly commute with itself. So this gives you the first example of a circle commuting operator that is not strictly commuting. So the OPE for this circle operator would say A of z and A of w has a leading term of z minus w to the minus 2. So from this you can read off the circle product of A and with itself. This says, for example, that A circle 1 is 1, A circle 0 is 0, and all the other circle products are either universal or they are 0. Okay, so this gives you both an easy way to construct a CCA. So once I have A, this shows that A generates a CCA. Okay, a circle commutative algebra, because it circle commute with itself. So Dong's lemma implies that this generates a CCA. Moreover, you know this OPE formula allows you to calculate all their circle products. Okay. Next, I want to introduce the notion of a left regular module of a CCA. So what is a left regular module? So this will be defined as follows. To every operator in a CCA script A, I assign an operator that acts on itself, which I call A hat. Okay, A hat, and the formal variable is called zeta. How is A hat zeta defined? Well, so this is supposed to be an operator on A. So on a test vector B, the action is given by the right-hand side of this formula. Is the coefficient of this power series in zeta is given exactly by the n circle products. Okay. So this define an operator on A, and if you start off with a homogeneous operator, then A hat would also be homogeneous of the same way. So moreover, it's not hard to show that this linear map, which I call rho, is a circle algebra homomorphism. Okay, meaning it preserves all circle products. So this turns out to be a faithful module, and it is called a left regular module of A. An old theorem that goes back to the 90s. If A is a circle commutative algebra, then you could look at this quadruple, sorry. You can look at the algebra, the underlying algebra A, the identity operator in A, the del, the formal derivative del, and the left regular module. So look at this quadruple. This quadruple form the claim is that this quadruple form a vertex algebra in the sense of Borchardt and FLM without the Virasoro. And it turns out that the converse is also true, that every vertex algebra in the sense of Borchardt and FLM naturally give rise to a circle commutative algebra. Okay. So this theorem shows that the theory of CCA and vertex algebra are in fact logically equivalent. But of course, one important difference is that CCAs are technically much easier to work with and much easier to use as a tool to construct examples, as I've illustrated earlier. Another advantage of CCA is because of its the formalism is based on the fact that this class of algebra mimics ordinary commutative algebra, except that, you know, unlike ordinary commutative algebra where you have exactly one product, meaning the usual associative product, a CCA contains infinitely many products, namely this circle product indexed by an integer. But these non-associative products combine together to form a commutative operator product in the sense of matrix coefficient. So it's a sort of a subtle kind of commutativity that comes from an infinitely many non-associative product. Okay, so this point of view allows us to view vertex algebra as higher analog of commutative algebra in a sort of a very suggestive way. Many questions from commutative algebra can now be carried over to this setting, at least as questions and perhaps conjecture, and perhaps you know, provide a tool to answer some of them by using classical tool from commutative algebra. So this point of view has been very useful and fruitful in the past couple of decades. All right, now comes the construction of the Moonshine VOA that goes back to FLM. Again, I'm going to explain it in the CCA formalism, but everything I say here it has an equivalent, if not a strict copy from the book of FLM. Okay. Okay, let L be any even lattice and define the vector space of V subscript L. to be the tensor product of two spaces. First one is it's called FL. What is FL? FL is nothing but the polynomials, the space of polynomials in infinitely many variable, alpha of -1, alpha of -2, and so on. So indexed by negative integers, where the variable alpha is indexed by the lattice itself. And with the prescription that each of these variables is linear in alpha. Okay, so for example, you take two elements of the lattice, alpha plus beta, then the coefficient, the variable alpha plus beta of -1 is equal to alpha of -1 plus beta of -1. Okay, likewise with the other variables. Okay, so this is nothing but the vacuum Fock space representation of the Heisenberg algebra, as sort of the multivariable Heisenberg algebra, defined by the commutator relation in the middle of this page. And the coefficient, the variable alpha of n, acts on the Fock space by the usual creation and annihilation operator. So the positive mode will act by annihilation, and the negative mode act by creation operator. I'll say something about the zero mode next. All right, so there are two factors, F and L and C of L. What is C of L? C of L is nothing but the group algebra of L, okay? And to draw the parallel with the physics construction, L played the role of something called the momentum lattice, parameterizing the winding mode of the bosonic string on a real, propagating on the real torus. Okay? All right, so as I said, alpha of n, I can now view alpha of n as an operator of the tensor product. Namely, just let alpha of n, when n is non-zero, to act on the left-hand side factor FL. The zero mode f of 0 will act on the group algebra factor C of L by the formula given by this diagonalizable operator. So f alpha of 0 acts diagonalizably on the group algebra, and the eigenvalue is simply the inner product of alpha with another vector in the lattice beta. Okay. Okay. Next, I want to define a vertex operator on the vector space V of L. So formally is given by this formula, what I call E subscript alpha of Z, and it's defined by the product of 4 elements. Okay. The last two are self-explanatory, so these are just formal exponential sums of a Laurent series whose coefficients are linear operator. Okay, so you notice that the rightmost sum is the sum over positive integer. So most of these operators are annihilation operator. So on any vector in V of L, this operator would return a finite sum. Okay, and the second exponential sum over the negative integer, and the coefficients are all creation operator. So the composition makes sense because the first exponential sum gives you a finite sum, and so you can take the second sum and act on this finite sum and produce now an infinite sum. The third term, which I call Z of to the alpha 0, if you recall, Z of 0, alpha of 0, this zero mode acts diagonalizably on V of L. So therefore, on any given test vector, Z of alpha 0 would just produce a finite sum, in fact, a Laurent polynomial. So once again, the composition of the 3 last vectors makes sense because you're composing an infinite series with a Laurent polynomial. And finally, e to the alpha. E to the alpha is simply an element of the group algebra acting by left multiplication on the group algebra. So it would take e to the alpha, e to the beta to e to the alpha plus beta, okay, as expected. All right. So what I've shown you is that I've defined an operator on V to the L. Okay, in the sense I defined earlier. So this is an operator that takes a test vector and replace it and send it to a Laurent power series. This, in fact, is precisely the physics counterpart, the mathematical counterpart of what physicists call vertex operator, introduced in the early 70s. Notice that I also have a sign convention, a sign plus or minus in front of this definition. I don't want to get too much into the technical detail, but let me point out that the sign is defined according to which subspace of the of V of L it acts on. Okay, so the sign is determined by a particular two cycle that define a group extension of the lattice L by the two element group Z mod 2. That two cycle is important to make sure that these vertex operator actually circle commute among themselves. Okay, so that's sort of the technical point. All right, so here's the lemma. So with the proper sign convention in place, then one can show that whenever the inner product of two lattice vector alpha and beta is non-negative, then the two corresponding vertex operators strictly commute. And in the other case, when they are negative, the inner product is negative, then they do not strictly commute, but rather they circle commute. Okay, a circle commute. So this shows that this set of vertex operator E alpha generate a circle commutative algebra, which I denote by A subscript L. Okay, A subscript L. Okay. Next, to move on to construct the Moonshine VOA, let us now specialize L to the least lattice. Okay. So least lattice here is denoted by boldface L. Now this lattice, of course, has the standard involution that sends alpha to its negative. A of L has a module consisting of what FLM call twisted vertex operator. So this was introduced mathematically by FLM in their 1988 book. And it's sort of something that physicists have been using also in the 80s to talk about orbifold. So I'll refer you to a set of notes by Paul Ginspark in 1990 for the development of twisted vertex operator in physics. In any case, these are not strict vertex operator, but they are vertex operator involving powers of instead of summing over integer power, they involve summing over half integer power. Okay. All right. So without getting into too much of the technical detail, let's just focus on this involution and the case when L is the least lattice. So the least lattice is just another, at this point, another even lattice. And least lattice happens to be rank 24, and it happens to be unimodular. So you go through this FLM construction and construct your CCA or vertex operator AL. Now the involution of course induces an involution on the vertex algebra. And so you can take the fixed point subalgebra, which I call A subscript 0. Okay. Now you can take the sigma invariant subspace or A1 of the twisted sector. And that turns out to be an A0 module. Okay, it's a module over this 6-point subalgebra. And FLM take the direct sum of these two sector, so A0 and A1. All right, so A1 being again the sigma invariant subspace of this particular twisted sector. Okay, so you take the direct sum of these two spaces, and you call it V natural, or equivalently call it A natural. Okay. Now, the claim is that the space of operators, A natural, is naturally a circle commutative algebra. And hence, by the logical equivalence, this is a vertex algebra. Okay? And this is how you see it. So first of all, A0 and A1 are both A0 module. So A0 and so the X, when you act through this natural action, so you know how to multiply operator from A0 and operator from A1 in this sense. Second, both A0 and A1 are cyclically generated. They're generated by a single vector. Okay. A0 can be generated by the identity operator, and A1 is generated by a particular lowest weight twisted operator, which I call A1. Okay, turns out that there's a unique twisted lowest weight operator up to a scalar multiple. So you take these two elements, and in fact, the lowest weight twisted operator can also be viewed as an intertwining operator, in the sense that it maps A0 to A1 in the formal power series sense, and as such, it satisfies the condition that the matrix coefficient of any element of A0 with A1 is equal after analytic continuation with the other product. You know, when you take the product the other way around, A1 with with this operator B0. So this means that any operator from the A0 sector commute with this particular highest weight twisted operator A1. Okay. From this, you can show that it uniquely determines the action of A1 on A0. So every element of A1 would send an element of A0 to an element of A1. Okay. Okay. So this allows you to now completely determine all circle products of the two sector A0 and A1. Okay. So if you take any two operator, B0 in the zero sector and B1 in twisted sector, their circle products are now completely determined by the observation I just mentioned. And the result would give you an element of A1. Okay. And finally, if you look at the operator product expansion of A1 and with itself, and this is calculated in the famous book of FLM in chapter 9. And they show that the reinterpreted in terms of the circle product formalism. They show that the circle product of A1 with itself are all elements of A0. Okay, so that means if you take operator product for two elements in A1, you land it back in A0. So this means that A natural is closed under all circle products. Okay, and of course it contains one because the A0 contains the identity operator. So this shows that again by the result I mentioned earlier, A natural now is circle commutative algebra. Okay, because any two elements circle commute. All right. All right. So now that we have gotten the vertex algebra, or a circle commutative algebra A natural, or in FLM notation, they call it V natural. You have to show that this is correct. You know, this is a correct Moonshine candidate. Well, one piece of evidence that one piece of very strong evidence that FLM was able to prove was to show that the Q trace, to calculate the Q trace of the identity operator of this particular module. In fact, they calculated, you know, this the Q trace given by the genus 1 partition function of this vertex operator, where the Virasoro structure is given by the stress energy, the standard stress energy tensor, which I write here in this slide called T of Z. Okay, and you take the 0 mode T0, and you do the formal Q trace. So FLM spent many pages in their book to prove that this Q trace is in fact equal to the modular function J of Q. All right. Next, well, what about the Grice algebra? Well, if you look at the weight 2 piece of this candidate from Moonshine, and look at the circle product, circle 1. The circle 1 is a product that takes 2 elements of A2 back to itself. So circle 1 becomes a bilinear operation on the weight 2 space of this Moonshine module. And the Moonshine module by FLM's result, this weight 2 subspace by FLM result has the correct dimension of the Grice algebra, namely 196,884. And they show that in fact this circle product recovers the product, the non-associative product that Grice introduced in 1980. Okay. It is also known that the vertex algebra A natural is something called a holomorphic vertex algebra. That just means that its regular, its left regular module is its unique simple module. So this is a result that goes back to Dong in 1993. Okay, so this VOA is very special in that it has a unique simple module, namely the left regular module. Okay, all right. So as I said, so V natural or A natural is an example of a holomorphic VOA. And well, so then the question is, what are the other holomorphic VOA with the same property? You know, with this property that it has a unique simple module. So Shalikan in his paper in 1988 start to answer this question. So he outlined a series of steps to construct or to classify to this class of holomorphic VOA. Okay, and he claimed that the first property of such a VOA must be that the Virasoro central charge must be a positive integer divisible by 8. Okay. But much of his paper is to mathematicians require some work. So in fact, there were a series of papers that follow up on Shalikan and to produce proofs of many of Shalikan's claims. So for example, for central charge 8, Dong and Mason showed that the only example is the VOA based on the even lattice, the E8 root lattice of E8. Okay, And for C, for central charge 16, there are exactly two examples. The E8 cross E8 lattice plus the SO16 lattice. Okay. So again, these are results from the Don Mason paper. So the most interesting case, therefore, is C equals 24. The next interesting case, I should say. So what's going on for C equals 26? Well, so you make an additional assumption. You assume that that the vertex operator V is of CFT type. So what is CFT type? Simply means the highest weight space, the V0. Okay, well, in this case, the lowest weight, V0 is one-dimensional. If you make that additional assumption, then Scheller can show that the Q trace must be of the form given by the J function up to an additional additive constant. And that additive constant must be the dimension of the weight 1 space. Okay, V of 1. This is Scheler's result. Okay, so again, he uses conformal field theory argument. Okay, so then the question is, well, what are the possibilities for V? Okay, this is only one piece of data about V. It just gives you the Q character of V. Well, there are further results. So for if there turns out that V1 has for the CFT type VOA, V1 has a natural Lie algebra structure that I observed along with Scheller in the late 80s. Okay, so V1 has a natural Lie algebra structure. So there for C equals to 24, Scheller can further show the following: if V of 1 is the abelian Lie algebra, is an abelian Lie algebra, in this case, well, all right. So there are two possibilities. V of 1 is either an abelian Lie algebra or it's a semi-simple Lie algebra. Okay. In the abelian case, it turns out that it would have to, then L would have to be the least lattice. And when L is, when V of 1 is non-abelian, turns out that L must be one of the other Niemeyer lattices. Okay, so remember that their least lattice is one of the only one of the Niemeyer lattices. So when V of 1 is non-abelian, semi-simple, then L must be not a least lattice, but one of the other Niemeyer. And that particular Niemeyer is characterized by the associated root system of the Lie algebra G. Okay. And Scheller further went on to consider the possible structure of the semi-simple case, and he uses the representation of the affine vertex algebra of G hat, and how you can use that representation to form character that reproduce the Q trace of V, namely the modular function plus this dimension. And there he would have to appeal to the classification of unitary G hat module that goes back to Katz, Frankel and Katz and Katz-Peterson, among other people. Okay, so this is how Scheller can try to pin down the structure of C equals to 24 holomorphic VOA. So he showed that there are exactly 70 possibilities together with 71 possibility. So 70 possibility aside from the V natural. So V natural corresponds to the case when the weight 1 space is identically 0. So the one that FLM constructed. And Silicon went on to conjecture that these are the only possibilities, 71 of them altogether, of C equals to 24 vertex, holomorphic vertex algebra. And over the last 26 years or so, a lot of people have worked on this conjecture, and this is now essentially a theorem. So the work notably done by Van Akkeren, Lam, Moeller, Scheikhauer, Shikamura, and many other people. So this joint work have shown that the other 70 cases are now settled. The only exception is the Moonshine. So still, people still don't know whether or not when V1 is 0, meaning if that Lie algebra attached to the vertex operator algebra, holomorphic vertex algebra V is 0, is the Moonshine the only one? We know Moonshine is one of the examples as conjectured by Igor Frankel in 1987, but we still don't know whether this is the only example. Okay, so this is still a very much an open problem. Okay, I have about 30 minutes, so the next topic I want to talk about is the parallel between a vertex operator algebra and commutative algebra. Okay, so what is as I said, vertex algebra are natural generalization of commutative algebra. And there are also several functors that goes backward. Vertex algebra give rise to certain commutative algebras. One of the most important one is defined by Zhu that goes as follows. So take a vertex algebra script V and consider the subspace generated by all -2 circle product. Okay, so the subspace spanned by all -2 circle product. So this is the -2 circle product is nothing but a weak product of del A with B. Okay, and then you take the quotient of the V by this subspace. And you get a natural map from V to the quotient. It turns out that the quotient is a commutative algebra where the product is simply the weak product. Okay, this is now called the Zhu's commutative algebra. So to every vertex algebra, you can attach to this natural commutative algebra due to Zhu. One example. So take the Heisenberg algebra generated by a single field, as we did before. Then the Zhu algebra turns out to be just a polynomial algebra in one barrel, generated by the image of the generating field alpha. Okay. More generally, generalizing this example, one can show that if V is strongly generated, then the Zhu commutative algebra is also generated by the corresponding strong generator. What do I mean by strong generator? Strong generation. I say that V is strongly generated if V is spanned by the weak product of the set along with their formal derivative. Yeah, so you say that VOA is strongly generated by a set if you can span it by just the weak product of the set and their formal derivative. Okay, so you introduced something called C2 cofiniteness condition. You say that a vertex algebra is C2 cofinite or Lie if his commutative algebra is finite dimensional. Okay, it's finite dimensional over C. So it's characterized by the finite dimensionality of that associated commutative algebra. One can show that if V is Lie, then it has finitely many simple modules. This plays a key role in Joule's modularity theorem that he proved in his thesis, which I won't have time to go into. So for many years, people conjecture that rationality and C2 cofiniteness are actually equivalent. But later, a few people have come up with constructed a counterexample, a so-called triplet algebra, that shows that that example is C2 cofinite, but it's not rational. But up until now, people still believe that one direction of the implication is true. Namely, any rational VOA should be C2 cofinite. But this is still an open problem. Arakawa, in the last few years, and his collaborators has done important work in this direction. So Arakawa, in particular, introduced the following object. So one looks at the scheme spectrum of Joule's commutative algebra, and the maximum spectrum of this commutative algebra. The maximum spectrum is called the associated variety. It turns out that this associated variety have many important implications about the representation theory of E. Okay, so Arakawa and company introduced the following generalization of the notion of C2 cofiniteness, what they call quasi-Lis condition. So you say that V is quasi-Lis if this associated variety, which actually turns out has only finitely many symplectic leaves. The Poisson variety comes from the fact that this variety has a Poisson bracket defined by the notion of symplectic leaves. Let me point out that the notion of symplectic leaves for Poisson variety was developed by an earlier paper of Brown and Gordon for a large class of algebra, including something called the symplectic reflection algebra introduced by Eddinghoff and Ginsberg in the early 2000s. The stratification of the symplectic leaf turns out to give very deep insight into the representation theory of the algebra in question. And Arakawa used this construction to prove a very important theorem, which I'll explain in a moment. So just an example, Arakawa showed that if G is a simple Lie algebra and K is an admissible level, then the simple affine VOA, LK of G, is quasi-Lis in this sense. So there are only finitely many symplectic leaves. So quasi-Lis turns out to be a natural generalization of the C2 cofiniteness condition of Joule. So Arakawa proved that if V is quasi-Lis, then it has only finitely many simple modules. Okay. Okay. Next, moving on to another parallel between vertex algebra and commutative algebra. I want to talk about the Hilbert problem, or Hilbert finiteness problem. So a famous theorem of Hilbert in theory of commutative algebra says that if you have a reductive group acting on a commutative C algebra, that is finitely generated, then the invariant ring is also finitely generated. Okay, I won't have time to get into the proof, which is sort of outlined in a few steps here, and this transparency will be posted. But I think people who work on invariant theory knows the proof. In any case, I want to move on to the vertex algebra analog of Hilbert problem, and ask the following question, sort of the analogous question. Suppose I have a strongly finitely generated vertex algebra V, and a reductive group acting on it as an automorphism. The question then is the invariant subalgebra, the fixed point subalgebra, also strongly finitely generated? So this would be the exact parallel of Hilbert's problem for the class of a strongly finitely generated algebra. Okay, my former student Andy Linshaw and his collaborator Quasi-lisse has written a long series of papers on this subject, and let me briefly outline some of the progress that they have made. So first, let me point out that in general, that if V, if you have this question I asked, in general, this the answer is actually false. Okay, you don't have the nice Hilbert theorem like you do in the case of commutator algebra. For strongly finitely generated algebra, vertex algebra, the similar statement is false. So this is the simplest example. Take the Z2 action on the abelian vertex algebra generated by a single field. So alpha. So this is nothing but a polynomial algebra, and Z2x by just the usual reflection. Then it's not hard to show that by direct calculation that the fixed point algebra cannot be strongly finitely generated. Okay, so it cannot be spanned by just the ordinary weak product and their derivative. However, it is still expected that this holds, the Hilbert theorem holds if V is if you have an additional structure, namely if you assume that V is a simple algebra. Yeah, it's a simple algebra. There's no two-sided ideal for any reductive group G. As I mentioned, Linshaw and Quasi-lisse have made a series of progress in this direction. So let me mention some of them. For simple VOA of the following type, if V is a free field algebra, namely these are VOA generated by field whose OPE involves only scalar terms, only constant scalar terms. These are called free field algebra. So the simple ones, they all have this property, this strong finite generation property, a la the Hilbert problem. Another class is you take the affine vertex algebra, VK at genetic level, or their super algebra analog. Then one can show that they also the invariant subalgebra is also strongly finitely generated. Another class is given by something called the W algebra. The W algebra can be roughly characterized as follows. You start with a say simple Lie superalgebra G, and you take any nilpotent element F in G. That determines a family of vertex algebra called W algebra, depending on a parameter called the level, denoted by K in this notation. The formal construction goes through something called the Drinfeld-Sokolov reduction of BRST complex, which is a rather technical construction, which I won't go into. In any case, Linshaw and Quasi-lisse show that for this class of algebra, the finite generation, the strong finite generation property also holds. And one can also easily show that any tensor product of finitely many VOA is also falls into this category. So this shows that for this many large class of simple VOA, the answer to the vertex algebra Hilbert problem is affirmative. Now, all of these vertex algebra that Linshaw and collaborator studies have admit a certain limit in which the problem can be handled using classical invariant theory. In fact, much of their proofs rely on classical invariant theory. The basic tool is the so-called first and second fundamental theorem of invariant theory, abbreviated as FFT and SFT in this transparency. For a finite dimensional G module. Okay, so let me briefly recall what these two theorems says. So FFT says the following: that if you have a finite dimensional G module, the explicit generating set for the invariant ring, where vi is given by the polynomial in copies of the module in question. Okay, call it vi. So every explicit generator can be obtained from this a ring of this form. And the second fundamental theorem tells you how to calculate the ideal of relations among these generators. So that's what the two theorem says. Now, so the question is, for which examples do you know that these two statements are hold? Well, it turns out that there are only very few and far between cases where these theorems are known. So the three notable cases are the ones that is very classical, that goes back to Val for the standard representation of classical groups, and then Procesi many years later proved a similar statement for similar statements for adjoint representation of classical groups, and then there's a paper of Schwartz that does it for the 7-dimensional irreducible representation of the exceptional group G2. In these cases, the explicit minimal strong generating set of the invariant theory of the invariant VOA can be given. Okay, using these classical results. So this Hilbert problem has some application in the coset construction of Goddard, Ken, and Olive, and Franco and Zhu. So, for example, given the vertex algebra and the vertex subalgebra A, you could first define the so-called coset subalgebra given by the commuton of A in V. So what is this? So this is a subalgebra of V that strictly commute with the subalgebra A. Okay, so you have a vertex algebra V, an ambient vertex algebra V, and a subalgebra A. You look at all elements of V that strictly commute with all elements of A. What you get is another subalgebra, sub-VOA of V, okay, which we call C here. So now you get a pair of subalgebra of V, A and C. You can form the tensor product A tensor C, and you can map it, you can embed it back into the vertex algebra V in the obvious way. You just take two elements, one in A, one in C, and just formally multiply them. Because they commute, the formal multiplication makes sense. Okay? This embedding turns out to be a conformal embedding, meaning it respects the Virasoro structure. So what this does, it gives you an interplay between the representation theory of three algebras, a pair of subalgebras A and C, and the ambient algebra C. Okay. Okay. Here's an example. Take A to be the affine sub VOA, the affine VOA VKG. Okay. And if you have another vertex algebra V that contains A as a subalgebra, then you can talk about the commuton, and the commuton just turns out to be the invariant subalgebra with respect to the positive part of the loop algebra. Okay, what I call G of T. So this is the set of all polynomial in one variable T whose coefficient is in G. So this is a Lie algebra in a natural Lie algebra acting on the vertex algebra V. You look at this invariant subalgebra, and the statement is that the commuton is nothing but this invariant subalgebra. So therefore, the commuton, studying the commuton becomes an invariant theory problem, albeit for this infinite dimensional, Lie algebra. Now, oftentimes so one question is, when is this invariant subalgebra strongly finitely generated? So it turns out that for this question, one can look at a second VOA. Okay, so let me explain in one example. Consider the W algebra I mentioned earlier, associated to a simple Lie superalgebra G, and a nilpotent element of G. Then Kreutzig and Linshaw recently, or in fact, they just posted a paper that proved that for this particular W algebra, you can find a sub VOA also of affine type associated to another Lie algebra G prime, such that the invariant subalgebra of the W algebra with respect to G prime reproduces the commuton subalgebra. Okay, it reproduces the commuton subalgebra. So well, they call it CK here, and that this subalgebra is strongly finitely generated, provided that K is generic. Okay, so so in other words, this theorem implies an affirmative answer to the Hilbert finite generation problem for this class of vertex algebra. They call it WK. Okay, and this result allows you to give very explicit description of the W algebra, because it allows you to write it, in terms of an invariant, in terms of invariant theory, and it also allows you to do various coset, give various description of the coset construction of these W algebras. All right, so I have about 10 minutes left, so I'm going to now move on to my the speculation section. So I want to spend a few minutes just mentioning two things that Greg Zuckerman and I came up with in the early, well, both in the 90s and in the early 2000s. So what we did is that we proposed a cohomological construction of the monster group as follows. Well, it's more like going through a Lie algebra. Not so much the focus isn't so much on the monster group, but rather on the Moonshine VOA. Okay, it allows you to produce a Lie algebra from a Moonshine VOA or something similar to Moonshine VOA. So, for example, one of the Charlecon's VOA would also produce some new examples. All right, so the construction is roughly goes as follows. The main ingredient is the so-called BV algebra of myself and Zuckerman, which we constructed in the early 90s, and the Moonshine VOA, which I illustrate earlier. A natural. So what do? So you take the Moonshine VOA, and you take any other VOAV, script V. You tensor them, and then you stick it into the something called the semi-infinite topology of the Lie algebra Virasoro, and take the relative cohomology with relative to its center. So this cohomology theory was introduced by Fagan in the mid-80s. So many people have studied it, and we apply it to this particular case. Okay, so the coefficient of this cohomology is now the Moonshine tensor with an arbitrary VOA. The Moonshine being the fixed object in this construction. We call this graded cohomology group the Moonshine cohomology functor. So it is a map from it is a functor from the category of VOA to the category of graded vector spaces given by these cohomology groups, this semi-infinite cohomology groups. Now, one trivial observation: these cohomology groups are all zero unless the argument you stick in, the V, has Virasoro center charge exactly equal to 2. Okay, because this cohomology vanishes unless the center charge add up to 26. And here's a result that goes back to the 90s. For any VOA, this Moonshine functor gives you something called a Batalin-Vygotsky algebra. What this is a sort of an odd version of a Poisson algebra with the following property. The degree 0 piece, the M0, is naturally a commutative algebra with respect to the weak product. And M1, the degree 1 piece of this algebra, of this group, happens to be a Lie algebra with respect to the Lie bracket. Okay, so so M star is a pretty complicated object. One piece of it is a commutative algebra, one piece of it is a Lie algebra. In general, the higher piece also interact with the 0 and the first piece. And in fact, all the higher piece are modular over the degree 1 piece. Okay, the degree 1 piece as a Lie algebra acting on modules. And here's the most important example. Suppose you take the FLM vertex algebra, lattice vertex algebra, with respect to the unimodular rank 2 hyperbolic lattice. Then in this case, M0 is one-dimensional, and M1 turns out to be Borchert's monster Lie algebra. So Borchert introduced a class of infinite dimensional graded Lie algebras that generalize the Kac-Moody algebras. One of them is called the monster Lie algebra. So what I show you here is that this gives a cohomological construction of one of Borchert's Lie algebras. And if you use some other C equals to 24 in place of the Moonshine VOA, you also get some other of Borchert's Lie algebras. Okay. So because the coefficient of this group, one factor of it is V natural or CCA natural, and the monster group acts as an automorphism of A natural. It automatically acts on this functor as a natural transformation. So the monster group is in fact act faithfully as a group of natural transformation on this functor. The question is this the full automorphism group? So in 2003, Greg and I wrote a paper. We speculated that F1 is in fact a full automorphism group. It's sort of a very natural guess of what is true. Yeah. Okay. All right, finally, let me, since I only have 2 minutes, I don't think I have enough time to go through 4 pages. I think I have 3 or 4 pages of this construction. Something I call a chiral scheme, which is a way to attach
a chiral algebra, a scheme to every chiral algebra. I don't have time to explain the details of this because I'm almost out of time. But suffice to say that this allows you to attach a geometric space to every vertex algebra. Quite similar to the way Arakawa introduced his associated variety or associated scheme that attached to every vertex algebra a scheme of a commutative algebra. But what's new here is that I'm attaching a scheme to a circle commutative algebra. So this is a non-associative algebra, but commutative in sort of in the vertex algebra sets. So the point is that vertex algebra has enough structure that allows you to define the notion of scheme without associativity. It allows you to define the notion of prime ideals and so on, and therefore form a formal geometric space. Okay, so this is an ideal where that mimics what you would do in commutative algebra with prime ideals. So because we have a notion of prime ideals, you could use it to define the notion of closed sets and open sets, and all the formal property of classical scheme theory goes through for this class of CCA. And so with that in mind, you get what you get is from every vertex algebra, you get a formal scheme. Unfortunately, up until now, this is the first time I'm showing this in a public lecture. I came up with this idea in the early 2000s, but I never published it. But I thought this would be a good occasion to show it, to show this very cute construction. So far, I haven't been able to calculate many examples. Only 2 or 3 very simple examples where I can say something. In any case, so since my time is up, I'm going to stop on that note. And since the slide will be available online, I invite the interested audience to take a look at this construction, and maybe you have some idea how to analyze this new schemes. Thank you.
Okay. Thank you very much, Bong, for such a great talk on so many topics. So now I guess people can ask questions by submitting them through chat.
Right. So far, I didn't see any Q&A on the link. So I'm assuming
there were some at the beginning. I answered one question, but
oh, okay. All right. I presume TJ must be moderating that.
Yeah, there is a question. So somebody raised his hand. So let me unmute him.
Okay. Or maybe that somebody left.
No, he's here. He's here.
Oh. I didn't hear any questions.
Hello?
Yes. Yes. What, you have a question? I still cannot hear anything. Okay, let me see. Can you have a way to describe frac V in the coset construction? The simple answer is yes, but the answer is rather technical. So I'm not going to try to sketch it here. I will refer you to Linshaw's paper, which he actually just posted. So you can actually find it online. I think he posted it maybe like 4 days ago. So there you will find a construction of this G prime in his coset, at least in the context of the W algebra. I believe Linshaw is actually in the audience as well.
Yeah,
okay.
I think there is another question.
Okay. And what is the second question?
Yeah, it's let's see. So Zong Julin asks, can you have a
yes.
way to describe frac G?
Right.
Because okay, you already answered that.
Yeah, I gave a non-answer. Because of the technical nature of this construction, I like to refer him to the original paper of Linshaw and Kreuzek, which I as I said is posted 3 or 4 days ago. Okay. Any other question from anyone else?
Okay, so if there is no other questions, we would like to thank Bong for a great talk. So the slides will be available on the website in a few days. And thank you everyone for attending. Actually, there is another question.
That seems to be a second question, right?
Right. So let's see.
Boros Hansek. Okay, thank you.
Okay, thank you everybody.
Okay, so remark. Thank you. All right,
Okay,
thank you, Paul.